Welcome to a lesson with Dr. Powell. Let's look at some applications of dot product and cross product. Let's start with two vectors emanating from a point. Suppose it's the point 1, 2, and maybe -3. And you have another point here, 1, 5, and 2. And maybe another point, 2, -1, -1. All right. So between these points, we can draw some vectors. Let's call this one V. Let's call this one U. Okay. Now, for starters, let's find the equation of the plane that contains these two vectors. What describes a plane? Well, a point that's in the plane and a direction that's orthogonal or perpendicular to that plane. So to find a direction that's orthogonal to it, notice that these two vectors lie in the plane. If we take their cross product, we'll get something that's orthogonal or perpendicular to the plane. Let's compute what these vectors are if they were translated back to the origin. We can do that by taking a subtraction, this minus that, to find u. So for instance, we can have 2, -1, -1, and 1, 2, -3, and we subtract to get +2, and so -1 plus 3, and then we have -1 minus 2, so -3, and 2 minus 1, which is just 1. So we get u, we could think of it as being 1, -3, 2. V, we could do a subtraction there in that case. And we would just erase this right here. And we can kind of see what this is right here. This would just simply be 1 minus 1, which would be 0. And then 5 minus 2, which would be 3. And 2 minus a -3, which would be 5. Okay, so we end up getting this vector and that vector. Okay, so now we have these two vectors. Now to find one that's orthogonal or perpendicular to it, to both of those, we can take the cross product. And it doesn't matter which direction we use. If we started with u being first, then the orthogonal vector will come upward like this if u is done first. So I can write u up top, 1, -3, 2, and v down below, 0, 3, 5, and it can compute the cross product of the two vectors. So ignore this column, and we have -15 minus 6, so we get -21 for the first component. Remember, the cross product is always a vector with 3 components. Now, ignoring this column, we have 5 minus 0, so it's 5, but then switch the sign because it's in the middle, -5. Now we go here, we ignore this column, and we get just 3, 3. That's the cross product. Okay, so we know now we have a vector which is orthogonal to our plane. -21, -5, 3. Now, to have the equation of a plane, we're going to have different coordinates that are represented. So if x, y, z is in the plane, how can we come up with a condition that guarantees that it is in the plane? Well, that's what the dot product is for, because if this vector from the beginning point that we choose, maybe it's 1, 2, -3, that would be good. That's in the plane. From that beginning point to x, y, z, that vector should always be orthogonal to this vector. And that's the condition for being in the plane. And for this to be orthogonal to this one means that their dot product is 0. That is the equation of the plane, just the dot product equaling 0. It's great. So we just take the dot product of the vector that comes out of the plane that's orthogonal to it, and we dot it with a vector that lies in the plane, namely the vector between these 2 points, which is done by subtraction. X minus 1, y minus 2, and z plus 3. And the condition is that we want this dot product to equal 0. That's the equation of the plane. We can work out the dot product, which will simply be a number. Remember, dot product is not a vector, but a number. So we can multiply components here, negative 21 times x minus 3, 1, that is, minus 5 times y minus 2 plus 3 times z plus 3 equals 0. This right here is the equation of the plane. Notice that the coefficients of x and y, after we multiply it out, and 3, represent a vector that's orthogonal to the plane. That's always true. So if we had any plane at all, such as 2x plus 3y minus z is equal to 0, well, actually not quite 0. Let's make it equal to something else, equal to 10, say. Then what we could do is, after putting this in and doing some kind of finagling here, we could even think of this as 2x minus 5 plus 3y minus z, and we'd have equaling 0. Again, we'll have a dot product. And again, we notice that 2, 3, and negative 1 are the orthogonal vector. But we can just take that for granted. When we look at the coefficients in the equation of a plane, we can automatically identify a vector that's orthogonal to the plane, 2, 3, and negative 1. So what if we had a point that's off the plane? Suppose this is the plane, and we have a point that's not on the plane. Let's just take the point 1, 1, 1, and we know it's not on the plane because when we plug in 1, 1, 1, we have 2 plus 3 minus 1, which is not 10, so it's not on the plane. Maybe we're interested to know what the distance is, the orthogonal distance is from 1, 1, 1 to the plane. How would we do that? Well, again, we're going to use dot product, cross product information, and here we actually just need dot product. We already know a vector that's orthogonal, which is a real plus here. So to our plane in particular, we know that whatever this is, we could take a multiple of 2, 3, negative 1, and it would be along this line. So we can even imagine the vector along this line as being represented by 2, 3, negative 1. The vector might be pointing down this way or that way, but it doesn't quite matter. It's just along this line. Then what we need to do is we need to take this point and then any other point on the plane at all, it doesn't matter which one, and make a vector. Then if we take this vector and project it onto this line, we have that length. We can find the length there. The length of that projection is what we desire, the distance from that point to the plane. So how do we find that length? Well, let's do that. Let's find that projection. Okay, so we need to find a point that's on the plane though. How do we find a point on the plane? Just make it really easy on ourselves. Let's just plug in x is 0, y is 0. What does z have to be so we're on the plane? Well, we had 0 plus 0, so z would have to be negative 10. That is a point on the plane. So far, so good. So then if we find this vector, which is, well, this is 1, 1, 1, and the vector between 1, 1, 1 and that point, we just simply subtract and take this minus that to get this vector right here. So this minus, so that point really is this one. And you're finding the difference between those 2 points to find the vector between. So we end up getting 1, 1, and then 11, because 1 minus negative 10. So that's our vector that we want to project onto this guy. How do you project something onto something else? Well, whatever you're projecting onto, turn into a unit vector and take a dot product. It's as simple as that. So If we want to project onto this guy, make it a unit and then dot it with what we're wanting to project, what we want to project onto it. So take, find the length of this, which is 4 plus 9 plus 1, take a square root. Take the reciprocal of that and multiply that to 2, 3, 1, -1, and that becomes, this becomes a unit vector. And then we're going to dot that with 1, 1, 11 in order to find the projection. Here, when we do this, remember we're going to add because we're just going to get a number for a dot product, not a vector. So we're going to get 2, so we multiply, remember, plus 3 minus 11. So 5 minus 11, which would be -6. Hey, this actually tells us that our picture is a little skewampus. This is actually pointing downward, but it is okay. We can just take the positive of the projection. Notice it's going to be negative because it's over here. It's projecting onto the line over here when it's really, when this vector is really pointing in the other way, but we're okay with that. So we can just take the positive of this. 5 minus 11 is -6. We'll just take +6. +6 divided by this, which is square root of 14. And we're successful at finding that projection length, which is the distance between this point and that plane. Thanks for watching.